Lesson 1, Rhythm by the Numbers, or with apologies to George Gershwin, fractionating rhythm. Music is sound, so it's perhaps surprising that our discussion of math and music begins elsewhere, with rhythm. It starts with the easiest aspect of mathematics, namely counting. What is rhythm? Dictionaries agree that it is the placement and organization of sounds in time. It is the aspect of music comprising all the elements, accent, meter, and tempo, that relate to forward movement. In fact, the word comes from the Greek rhythmos, likely from rhyme, meaning to flow. A slightly more detailed definition is that rhythm is the subdivision of a span of time into perceptible sections, the grouping of musical sounds, principally by means of duration and stress. Look at a piece of sheet music. It has horizontal and vertical structure. The horizontal part is the rhythm. It's the length of each note and rest, the time signature, the number of beats, and so on. The vertical aspects are pitch, melody, that's notes going up and down, chords, and harmony. But that's for another time. Pun intended, of course. Although rhythm is difficult to define precisely, each of us has our own understanding of what we mean by rhythm, and I think we would all agree that rhythm is a fundamental component of music. Music without rhythm would be dull, like monotone speech. Perhaps the best known four-note motif in all of classical music is the opening of Beethoven's Fifth Symphony. 3 short repeated notes, and then a long note a little lower, technically a major third. Try it with 4 equal length notes, da, 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 da. It is recognizable, but it has no punch, no drive. The rhythm provides drama and suspense. Try it again the way you know it, and don't forget that it begins on the second beat. It starts with a rest. Da, 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 da. With rhythm, it has life. You can hear fate knocking at your door. Where does mathematics fit in here? Think about a two-dimensional graph. The horizontal axis often measures the passage of time. Counting is important. We count beats, we divide up beats into measures or bars. Beats in a bar create time signatures, and those are like fractions. Dividing notes and rests into smaller pieces also uses fractions. Putting all that together makes rhythm. Rhythm creates stability and tension. Rhythm, combined with melody, can be unsettling and settling. Why and how that works can be explained by simple mathematical ideas of addition, multiplication, prime and composite numbers, common denominators, and least common multiples. Can rhythm alone be music? Musical instruments, including almost all percussion instruments, have different pitches. Even a bass drum or bongo has volume. The closest to rhythm alone, aside from a rim shot on the edge of a drum, is just clapping. Would you consider clapping all by itself to be music? Listen to Steve Reich's 1972 piece called Clapping Music. Perhaps sound and aesthetic sensibility are enough to constitute music. Let's start with a question probably first asked nearly 1,000 years ago. In 1050, by Indian poet and mathematician Hema Chandra, how many ways can you put 1 and 2 beat notes together to build a rhythm of a prescribed number of beats? Hema Chandra asked this about syllables in poetry, but we can ask it about music. Call the 1 beat and 2 beat notes short and long. Musically, think about a quarter note and a half note. A 1 beat rhythm is very easy. There's only one way to do it, with a short note. A 2 beat 2-beat rhythm is also easy. 2 shorts or 1 long. How about 3 beats? Short, long, short, or short, short, short. Now, you might think the pattern is that the number of ways equals the number of beats. That's incorrect, because 4 beats can be done in 5 ways, and 5 beats can be done in 8 ways. So, what's the pattern? To see it clearly, let's put a silence, a 0-beat rhythm at the start. And of course, there's only one way to do that. So now we have that 0 beats, there's 1 way. 1 beat has 1 way. 2 beats, 2 ways. 3 beats has 3 ways. But now, 4 beats has 5 ways, and 5 beats has 8 ways. That's 1, 1, 2, 3, 5, and 8. Add the first 2 numbers, 1 and 1, to get the third number, which is 2. Add the second and third to get the fourth. 1 plus 2 is 3. Add the third and fourth to get the fifth. 2 plus 3 equals 5. So 5 beats would be 3 plus 5, or 8 ways. 6 beats would be 5 plus 8, or 13 ways. And 7 beats would be 8 plus 13, or 21 ways. We'll keep going. 8 beats. 13 plus 21 is 34 ways. Now this is a famous sequence in math. It's known as the Fibonacci numbers. Fibonacci gets the credit, even though his book that mentions them, called Liber Abaci, was published in 1202, about 150 years after Hemachandra's work. Why do Fibonacci numbers work here? Each 8-beat rhythm starts either with a short or a long note. If it starts with a short note, then there are as many ways to complete this as there are 7-beat patterns. If it starts with a long note, there are 6 beats to fill, so there are the same number of possibilities as there are for 6 beats. Thus, the number of 8-beat patterns equals the sum of the number of 7-beat and 6-beat patterns. 8 is the 7 and the 6. The number of possibilities grows very quickly as the number of beats in the rhythm increases. 12 beats can be done in 233 ways. Now, mathematicians love to generalize. What would happen to the possibilities if 3-beat notes were allowed? There is no chance of running out of rhythmic patterns. Splitting up a string of beats or notes. Run-on sentences are not just grammatical gaffes. They are difficult to understand. Can you understand written text that's longer than a few words if it has no punctuation? How do we split up a string of words? We use periods to denote sentences. How do we split up a string of notes? We use bar lines to denote measures or regular recurring groups of beats. Time signatures tell us how many notes to put in a measure. They look like fractions with a numerator, a number on top, and a denominator, that's the number on the bottom. The top number gives the number of beats in a measure. The bottom number indicates the length of each beat. So 3/4 time means 3 beats in a measure, each 1/4 long. Now that's usually waltz time. I bet Johann Strauss's Blue Danube Waltz is the first one that comes to mind, and I apologize for planting that earworm in your ear. And 4/4 time means 4 beats in a measure, each 1/4 long. It's called common time. It is very common. Another frequently used time signature is 2/4 time. I bet you can figure out the beats in this one. Now, the denominator isn't always 4. 2/2 has 2 half notes per measure. It is called cut time, since the numerator and denominator of 4/4 time have each been cut in half. These fractions also give us the terms whole note, half note, quarter note, eighth note, 16th note, and so on. If you want to show off, call them by their fancier names. Semibreve, minim, crotchet, quaver, semiquaver, demi-semiquaver, that's the 32nd note, and hemi-demi-semiquaver, the 64th note. Now, technically, there is a 256th note. It's a demi-semi-hemi-demi-semiquaver, probably the shortest perceptible one. If you're wondering whether there is also a breve, not just a semibreve, which is a whole note, the answer is yes. A breve is a double whole note. Now, what if we group the beats into triplets? That leads to 6/8 time, with 6 8 notes per measure. Other frequently used time signatures are 5/4, as in Gustav Holst's Mars from the Planets, and 3/2 time, used by Handel in his water music. 5/4 time adds suspense to the music. Two famous examples are Lalo Schifrin's Mission Impossible theme and jazz great Dave Brubeck's recording of the Paul Desmond piece, Take 5. George Gershwin wasn't the only one to write fascinating rhythm. There are rare ones too, such as 7/16 time. Igor Stravinsky loved obscure time signatures. In The Rite of Spring, he uses a whole bar for a single 32nd note and also uses an 11/4 bar. By the way, did you notice that the top number can be any whole number, but the bottom is a power of 2, 2, 4, 8, or 16. Modern composers, however, are experimenting with some very strange time signatures. Rhythmic patterns can influence a listener's feelings, from a relaxed lullaby to a snappier or hazier sound. Two classic examples are Ravel's Bolero and the habanera in Bizet's Carmen. Changing rhythms and combining rhythms. Our brains love patterns, but they like surprises too. Rather than maintaining the same rhythm throughout, composers will change rhythms to interrupt the normal flow of the music. It catches the listener off guard. Here's a property you learned in math a long time ago. 2 plus 3 equals 3 plus 2, and 2 times 3 equals 3 times 2. We say that addition and multiplication are commutative. The order doesn't matter. Now note that that doesn't work for subtraction or division. 3 minus 2 is not equal to 2 minus 3. 3 divided by 2 is not the same as 2 divided by 3. The commutativity property, that's a lovely word, makes 6/8 time very interesting. Since 6 can be written as 2 times 3 or 3 times 2, the beats in a measure can be thought of as 2 groups of 3 beats or 3 groups of 2 beats. We can count them as 1, 2, 3, 1, 2, 3, or 1, 2, 1, 2, 1, 2. Perhaps the best known example is in Leonard Bernstein's West Side Story. The song America has the lyrics, I like to be in America, okay by me in America, and so on. 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 1, 2. 2 groups of 3 followed by 3 groups of 2 is called a hemiola. The term comes from the Greek for 1.5, the ratio of the lengths of the 2 groups, which is 3/2. Hemiolas are used extensively in Western classical music. Some examples include Handel's water music, the hornpipe, which is the second movement of the Suite in D major, Dvorak's Symphonic Dances, Opus 46, number 8, uses them, Bach's 2-part invention in D minor, Debussy's Clair de Lune from Suite Bergamasque, Brahms' Intermezzo, Opus 118, number 4, all of these use hemiolas. In each of them, the ear detects the 2 rhythms, which makes it feel like the music is speeding up. Would other pairs of rhythms based on this commutativity property work? Well, instead of 2 times 3 equals 3 times 2, what about 2 times 4 equals 4 times 2? It's not very interesting, since 2 fits into 4, so you wouldn't really notice a change of rhythm. And 2 times 5 being 5 times 2, would have rather long groups of notes to think about. But this one would work. 12 would be 3 times 4, or 4 times 3. There you have it. Commutativity in math produces feelings in music. Polyrhythm. Now, what if there are different rhythms in different parts simultaneously? That's called polyrhythm. It could be as simple as playing quarter notes in the right hand and half notes in the left hand. But more interesting is playing triplets, groups of 3 notes in the right hand, while the left hand is playing 2 notes. The triplets are like saying the word orchestra or symphony orchestra. The pairs of notes are like saying maestro. We call this 3 against 2. It's a bit like a hemiola, except that the 2 parts are played at the same time, rather than one after the other. The combined rhythm is like saying orchestra pit, or hamburger bun, or nice cup of tea. Rachmaninoff used it to great effect in his prelude for piano, Opus 23, number 4. In the third movement of Tchaikovsky's Piano Concerto number 3, the piano is in 3s, while the orchestra is in 2s. In Schubert's Ave Maria, the piano is in 3s, the voice is in 2s. And Brahms' Intermezzo, Opus 118, number 2, provides another wonderful illustration, particularly in the second or the middle section. Polyrhythms give the listener an unsettling feeling of instability. The 2 rhythms are like competing forces, providing dynamic tension. And then they resolve back into normal rhythm. Where's the math? It's in calculating the polyrhythms. Divide one note into 3 parts and another into 2 parts. Putting them together is like adding fractions. You need a common denominator, which is the lowest common multiple of the 2 numbers. With 3 against 2, the lowest common multiple is 6. To add 1/2 and 1/3, the 6 serves as the lowest common denominator. That means 1 bar of 3 against 2 divides up the spaces between the notes into 6 pieces. To play 3 against 4, the lowest common denominator is 12. So you need to fit 12 pieces together in a bar. The rhythm is like saying, play the whole piece faster, or play the right hand louder. That's 3 against 4. Chopin loved polyrhythms. His Nocturne Opus 9, number 3 has, in a span of 5 bars, 3 versus 5, 3 against 7, 3 against 8, 3 against 1, 3 against 9, 3 against 6, and 3 against 8. It's complicated. His Opus 9, number 1 Nocturne has 11 versus 6 and 20 versus 6. 11 versus 6 would require a lowest common multiple of 66. Samuel Barber's Excursions for piano number 3 uses 7 against 8. That's walk down the hall and try hard not to fall. The cadenza in the first movement of Grieg's Piano Concerto requires the left hand to play runs of 7 notes per beat, while the right hand plays the melody plus 8 notes per beat. To do this exactly, you would need to divide each into 56 very tiny pieces. Forget it. That's where musicality comes in. Musicians don't think explicitly about the math of polyrhythms, the fractions, and the common denominators. They just learn to do 2 things simultaneously. In Charles Ives' Fourth Symphony, polyrhythms are taken to their extreme. Different parts of the orchestra play completely different rhythms. Usually, 2 conductors are needed to perform the piece. Math shows how the piece is supposed to be played. The performer's feeling makes it work. Combining rhythm and pitch. In arithmetic, we know when one number is a multiple of another. If you put 2 groups of 3 objects in a row, they will match up perfectly with a group of 6 objects, but not with 5 objects. Consider a 5-beat rhythm, 1, 2, 3, 4, 5, and 3 pitches or notes, A, B, C. They won't match up. They would be out of sync until 15 notes had been played. With 5 notes in each bar, the pattern would repeat every 3 measures, or every 15 notes. Where did the 15 come from? Math. It's the least common multiple of 3 and 5, which is 15. The feeling one gets musically is that of turning over and over until finally getting back to the beginning. There are multiple examples in George Gershwin's Rhapsody in Blue. One of the main motifs only repeats every 15 notes. As the piece nears the end, a passage has 6 notes per bar, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, but built into an 8-note scale. In other words, the scale is wrapped in 6 pieces, which means it repeats every 24 notes. A match happens every 3 times up the scale. That rolling over is what gives the tension and instability. How does Gershwin end that passage? Brilliantly and surprisingly, with a pause and then a dissonant chord. Here's an example from the world of pop music. Listen to Bill Withers' 1971 hit, Ain't No Sunshine. The words, I know, I know, I know, are sung 26 times. Each is 3 8 notes long, but each bar has 4 beats. You really feel the turning over. In Richard Strauss's Till Eulenspiegel's Merry Pranks, the horn plays a 7-beat phrase in 6/8 time. So it only repeats after 42, that's 7 times 6 notes. Is that one of the Merry Pranks? Olivier Messiaen's Quartet for the End of Time has 2 rhythmic patterns that are 17 and 29 beats. So it takes 493 notes to get back to the beginning. That's a great metaphor for the end of time. Composers and musicians understand how rhythm influences feelings. Listeners experience it. Rarely does anyone think about the mathematics behind it, but now you can and will.